Hi, and welcome to Codex. Today, we are happy to have Michael Perlmutter from UCLA. Dr. Perlmutter earned his PhD from Purdue University in 2016 under the supervision of Rodrigo Banuelos. He has since held postdocs at UNC Chapel Hill and Michigan State, and he is currently a Hedrick Assistant Adjunct Professor at the Department of Mathematics at UCLA. Dr. Perlmutter's research focuses on problems in data science, probability, and harmonic analysis. Today, he'll be speaking on using graph Fourier transforms to do machine learning. Take it away.
Hello, everyone. I'm super excited to be here today. Thank you to the organizers for the invitation. As Emily alluded to, my talk is going to focus on machine learning on graphs and also directed graphs. And in particular, I'm going to be talking about how we can define convolutional networks based on generalized Fourier analysis. So, quick motivational slide. Graphs are everywhere. They're a natural model for a ton of different things and therefore are very important. So for anyone who's not familiar, a graph consists of a collection of dots, which you might view this as an atom within a molecule. And then there are edges between the dots, which you might view as representing like a chemical bond between the atoms of the molecule. Alternatively, a dot could represent an individual user in a social network such as Facebook. And there could be a line or an edge between these two users if they are friends on Facebook. And the list of things which graphs can model is nearly endless. You could use it to model email, for instance, or another example which has been widely studied in the data science community is citation networks, where dots will represent different scientific papers, and then there's an edge or a link between these two papers if one of them cites the other. So as an overview of my talk, I'm going to begin with introducing some examples of the different types of machine learning problems that arise in the context of graph structured data, and then talk about the basic definitions of convolutional networks for dealing with these problems, where the key technical challenge is going to be coming up with a proper notion of a convolution in the graph setting. Then after I spend the first third to a half of my talk talking about how great convolutional neural networks and graphs are, I'm going to then shift gears and focus on some of their limitations, but I'll also talk about how we can overcome them. Namely, what can be shown is that a lot of popular graph neural networks are effectively smoothing operators that try to make every neighbor on the graph as similar to their neighbors as possible. And in the harmonic analysis context, this corresponds to depressing high frequency information. So I'm going to talk about how we can modify standard GNN architectures using bandpass filters in the graph scattering transform in order to preserve this more rich variation in the data. And the other big limitation of CNNs is that they're unable to handle directed graphs. And so what I'm going to do is I'm going to present a simple solution on how we can modify most of the popular graph neural networks in order to handle directed graphs. So there's lots of different machine learning tasks we might be interested in graph structured data. And the first big family is so-called graph level tasks. So you could have graph classification where, for example, you might have a data set filled of 1,000 carbon molecules. Some of these are known to be related to cancer, whereas others are known to not be related to cancer. And you'd want to develop a predictive machine learning model that says, given some new carbon molecule, is this going to give me cancer? Alternatively, you could be interested in graph regression, where, for instance, you could know the formation energy of a bunch of lithium silicon molecules, which you might be using to design a battery. And you'd want to develop a new model where you're going to predict the energy of some new lithium silicon molecule and hopefully use this in like material science settings. As a third example is graph synthesis, where you might have a data set of a million different molecules. And the question is how can I come up with some new molecule which looks like it's a member of our data set? And this could be used, for example, in, say, drug development, where you're proposing like a new molecule, which you could hopefully then use in like novel medications. The second big family of tasks is so-called node level tasks, where for the purposes of this talk, I'm going to use the word node and vertex interchangeably to refer to the dots. And I'm going to use the word edge and link interchangeably to refer to the lines between the dots. And you might have a network, say Facebook, and you might know the political affiliation of some of the users, which are either going to be red or green. And then you want to develop a model which is going to predict the political affiliations of the other ones who did not specifically identify their political affiliation on their profile. Alternatively, you could have node clustering, which would be the unsupervised learning version of this talk, where you might be like, say, a business, and you want to split up the members of Facebook into different meaningful subgroups and maybe market different products to the different subgroups. A third family of tasks is edge level tasks. And the most popular of this is link prediction. And so here we have a social network. Some people are already friends, but you know what? Maybe Adam and Sophia actually already know each other. They just haven't added each other on Facebook yet. So we're going to say, you know what? There's not a link here yet, but we think there probably should be. And this is the mathematical basis for things like people you may know on Facebook or LinkedIn recommendations or other similar products. So this is the wide family of tasks, and these can be approached by many different methods. But what's become increasingly popular in the last, 5-10 years is to try to tackle these problems using deep learning. So as most people here are likely familiar, deep learning and convolutional neural networks are extremely effective for tasks related to, for example, image classification. And what they do is they apply a linear map and then a nonlinear map pointwise in an alternating fashion with some down sampling as well. But what they do that's particularly exciting is they don't just apply any linear map. What they do is they take advantage of the fact that the pixels of an image are arranged next to each other in like a regular Euclidean grid. And they use that to say, well, we're going to want to look at like local averages around each pixel. And we're going to do that. And then we're going to slide this local averaging around the image via convolution. And so the choice of convolution rather than an arbitrary linear map, it leads to much better networks, which are less prone to overfitting. But it also is very specifically based on the fact that the pixels are arranged in a grid. Now, graphs, they have a geometric structure, but it's not a Euclidean grid-like structure. So the question is how can we extend CNNs to graphs? And the main challenge is going to be to come up with a proper notion of convolution. Applying a pointwise nonlinear activation function will work the same way as before. And so there's basically two main approaches for defining convolution on a graph. The first one, which is primarily what I'm going to be talking about today, is the spectral approach, where we're going to look at the spectral decomposition, in other words, the eigenvectors and the eigenvalues of an appropriate matrix, which we'll call a graph Laplacian. And we're going to use that to define convolution in a manner analogous to the well-known convolution theorem from Fourier analysis. And there's also a spatial approach, which is defined directly on the graph via localized averaging. However, I'm not going to focus on that as much in my talk today. And then in either case, you can then construct a neural network through an alternating sequence of convolutions and nonlinear activation functions. Some basic notation before we start getting into it. We're going to let G equal VE be a graph where the vertices are going to be called V1 through Vn, and the edges are some subset of the graph. In the first half of this talk, we're going to assume that the graph is undirected, meaning that if there's an edge from vertex 1 to vertex 2, there's also a reciprocal edge back. This will change in the second half of the talk. And typically it's common to represent a graph through an adjacency matrix whose jkth entry will be equal to 1 if there's an edge from vertex j to vertex k and 0 otherwise. And we'll also be interested in a degree vector whose jth entry is the degree of vertex j, the number of people who are friends with vertex j, and a diagonal matrix with this vector along its diagonal, which we're going to call capital D. And we also look at neighbors of VK, where the neighborhood of VK is going to be the set of all other people on Facebook who are friends with user K, or formally it'll be the collection of J such that Vj, Vk is in the edge set. And in order to carry out these machine learning tasks, we are going to have to process signals over the graph. So in the Euclidean setting, a signal could be something like a sound, which would be viewed as a function over time. And what's done in Fourier analysis is these signals are decomposed into waves and oscillations. So in the graph setting, we need to think about how we can generalize this. And we're going to start with a function f defined on the vertex set. But since there's a finite number of vertices in our graph, we can identify this signal with a vector in r to the n, where the kth entry of our vector is the value of the function at the kth vertex. And what we're going to want to do is we're going to want to come up with a generalized version of Fourier analysis for processing signals of this form. And we're going to do this via the Fourier analysis based on a graph Laplacian. Now, I said a graph Laplacian, and that was a deliberate choice of words, because one of the things which is moderately annoying is there's no single agreed upon definition of the graph Laplacian. The first and perhaps most popular is the unnormalized graph Laplacian, which is just computed by subtracting the degree in the adjacency matrix. But there are also various normalized counterparts. And the symmetric normalized version is taken by left and right multiplying by the inverse of the degree matrix. And there's also a so-called random walk normalized Laplacian, which has a more natural probabilistic interpretation where you just left multiply by the inverse of the degree matrix. And I'm mostly going to focus in this talk on the unnormalized and the symmetric normalized graph Laplacians. And the reason for this is that these are going to be symmetric matrices, and so analyzing their spectral properties is more straightforward. Although I will talk about asymmetric matrices in a bit as well. So there's a couple of different ways that you can think about these graph Laplacians, and the first one is kind of an analog to complex analysis, where you can view the Laplacian of the Laplacian applied to a signal at a given point as a measure of how different is the signal at a given point from its neighbors. So at this red dot, what we can see is that the neighbors of the red dot are contained in the red circle, and the value of our signal at the red dot is bigger than all of its neighbors. And so therefore, the Laplacian applied to this signal is going to be positive at this point. On the other hand, the blue dot is smaller than the other points in the blue circle. So the Laplacian is going to be negative at this point, where I'm just going to use L without any sort of subscript if I want to be ambiguous about which one of the Laplacians I am using. The other way to think about this is to focus on the special case of the cycle graph. Because with the cycle graph, this is actually just the traditional discrete setting with periodic boundary conditions for all practical purposes. And you can compute that if you take the degree matrix, the degree of every vertex is 2. So you've got 2's along the diagonal. And the adjacency matrix is going to have -1s if you're like one step off of the diagonal. And what you can see is if you look at this matrix is up to a rescaling factor. This is exactly the discrete second derivative with periodic boundary conditions. The fact that you don't have the traditional 1/h² scaling term, this could be viewed as the motivation for why we normalize with some of the other Laplacians. And in particular, the eigenvectors of this are exactly the classical Fourier modes. So in other words, this is a natural basis for doing harmonic analysis on graphs. So for more general graphs, we're going to take this observation as our definition. We're going to look at the eigenvectors of the graph Laplacian. And it can be shown that the graph Laplacian is symmetric positive semi-definite. And so therefore you can choose these eigenvectors to be real. And you're going to define those to be the Fourier modes. You're going to look at the eigenvalues, and you're going to find these to be the associated frequencies. And you'll note that you can actually factor the graph Laplacian as U lambda U transpose, where U is a matrix with columns are the eigenvectors UK, and lambda is a diagonal matrix whose entries are the eigenvalues. And visually, we can compare these eigenvectors to the classical Fourier modes, whereas we see as we go from low frequency to high frequency, the signal varies more and more. And similarly, in the graph setting, high frequency eigenvectors are going to oscillate rapidly from one vertex to a next, whereas the lower frequency eigenvectors are going to be much more close to being constant. And so formally, you can note that lambda k can be computed by evaluating a quadratic form at the eigenvectors. And you can view this as our notion of the variation of a signal on a graph using the quadratic form associated to the Laplacian. So given this, we then formally define the Fourier transform or Fourier series by x hat of k to be the inner product of x with the kth Fourier mode UK. We note that since these can be taken to form an orthonormal basis, we have an inversion formula. And we also note that in matrix form, we can compute x hat to be U transpose x, or x to be equal to U x hat. Now, since the Fourier transform is invertible, that means we can define things based on the representation in the Fourier domain. And so we define the filtration of a signal x defined on the vertex set by a filter y to be the unique signal whose kth Fourier coefficient is the pointwise product of the Fourier coefficients of the original signal. Then we can plug this into our inversion formula and write y convolved with x is equal to the sum of y hat k x hat k times the kth eigenvector. Then we can plug in the definition of x hat of k and observe that we can again write this in a matrix form of U y hat U transpose x, where y hat is going to be a diagonal matrix with the Fourier coefficients of y along its diagonal. And this was exactly the class of convolutions which was used in the first paper that used a spectral neural network on graphs, which was introduced by Brune and al. 7 years ago. And this was a great paper that basically invented this overall family of methods of spectral neural networks for graphs. But since then, there's been a lot of work on overcoming the limitations of this network. And the biggest one of this is going to be that there's no direct relationship between this diagonal matrix y hat and the eigenvalues of your Laplace operator. And so the question is can we do something different rather than formally diagonalizing everything and then multiplying by this diagonal matrix in the middle? And the reasons we want to do this are threefold. One is if we're going to apply this, say, to a social network, social networks are massive. There are millions, if not billions, of people on Facebook and Twitter. And diagonalizing the Laplacian on a very large graph is extremely computationally expensive. The other issue is that the number of free parameters in this model is equal to the number of vertices. And this basically means that a network like this could be massively prone to overfitting. And like this would be equivalent in the graph setting of having one free parameter per convolutional filter for every pixel in your image. Just way too many. And the third issue is that since there's no formal relationship between this diagonal matrix y hat and the eigenvalues, there's going to be instability in your network where if you slightly change your graph, your model might learn completely different representations of signals defined on it. So there's a number of ways to overcome this, but the main idea is to use polynomials of the Laplacian. So, and by a polynomial of Laplacian, I mean if you take the polynomial x squared and you apply this to the Laplacian, that's the operator you get when you compose the Laplacian with itself. And what can be verified is that this corresponds to choosing y hat of k to be equal to the polynomial p applied to the eigenvalue of lambda k. And therefore, in matrix form, you can write that P of L is equal to U times P of lambda times U transpose of X. So the punchline of this slide is that defining convolution in the spectral domain like this is great and mathematically principled, but it has several practical drawbacks. But we can carry out these multiplications in the spatial domain without dealing with the heavy computational cost of actually computing all of these eigenvectors and eigenvalues. And this is the basis for two very popular graph neural networks. The first is Shebnet, where you assume that the polynomial is represented in a Chebyshev basis. This is building off of work by Hammond, which used Chebyshev polynomials to quickly compute graph wavelets. And then building off of Shebnet shortly thereafter was GCN by Kipf and Welling. And for people who are unfamiliar with the graph neural network literature, GCN is probably the most widely cited paper on graph neural networks. If you really like this talk and you say, I want to start working with graph neural networks, and you say, how do I implement a graph neural network in Python? When you type that into Google, the first thing that's going to pop up is going to be a tutorial from the good people at PyTorch Geometric. And the very first example they're going to do is they're going to have you implement GCN in the context of node classification. So more technically, basically what they do is they go through the Shebnet construction, they make numerous simplifications, assumptions on parameter settings, and also some approximations. And what they're able to derive at is a network that, well, spectral in its intuition, is actually a spatial network where it's basically multiplication by this matrix A hat. And this matrix A hat is taken by taking the adjacency matrix, adding self loops, adding the identity, using this to compute a modified degree matrix, and then multiplying by a normalization term corresponding to this modified degree matrix, then this modified adjacency matrix, then this modified degree matrix. And so this is all rather technical. So if you haven't seen this before, I don't expect these equations to be fully absorbed. But what I want to emphasize is that everything here is done using either if you're computing the signal at a given vertex, you're using either information at that vertex itself or its direct neighbors. So you're computing a highly localized averaging if you think about this in the spatial domain. Then what they do when they apply this to different settings is they use many different signals defined on the graph, x1 through xc, and they store this in a matrix called X, and then they use this designed matrix A and a trainable weight matrix theta. And what I really do want to emphasize, because this is a big difference between graph neural networks and traditional convolutional neural networks, is that the weight matrix is learned from data, but this A hat matrix is designed. Now, the context they applied this in was node classification. And in particular, it was semi-supervised node classification, which means that you know all of the vertices and edges of the graph. You know these features x1 through xc at every single node in the graph, but you only know the labels for a very small fraction of the graph. So what this means is they applied this typically to citation networks like Cora, where the goal is to try to figure out what type of paper something is based on who is citing it. In particular, what is the topic? And what subsequent analysis has shown is that what GCN does is basically trying to make the signal as smooth as possible. And this really makes sense in the context of these citation networks, because if my paper is about data science, then a majority of the papers I cite are going to be about data science. A majority of the papers that cite me are going to be about data science. So if you make me as similar to my neighbors as possible, you're going to get the right label most of the time. However, for more sophisticated data sets, maybe we want to do more than just a local averaging. So let's do a little bit of an in-depth analyzation of this so-called oversmoothing problem. the update rule is left multiplication by this A hat matrix and then right multiplication by a weighting matrix. And up to some technical approximation details, A hat can be approximated by this matrix called T, which is like a symmetrized version of a random walk matrix. It's also the identity minus 1/2 of the normalized Laplacian. So what this means is it really is a localized averaging operator. And you can check that it has the same eigenvectors as the normalized graph Laplacian. And it's well known that the normalized graph Laplacian has eigenvectors starting from 0 going up to 2. So due to the subtraction, this means that the bottom eigenvector is going to have eigenvalue 1. And all of the other eigenvectors of this diffusion matrix T are going to be strictly less than 1. In other words, what this means is that a multiplying by T leaves the bottom eigenvector, which depending on which Laplacian you're going to use is either a constant signal or a direct function of the degree, unchanged, and all other higher frequency information is going to be depressed. And so if you tried to build a really deep network, you'd be depressing this high frequency information more and more at every step. And partially for this reason, so-called deep networks on graphs typically only use 2 layers, because if you build a network too deep, you're going to completely destroy all high frequency information. So that's the limitation, and our solution to how to get rid of this is to use wavelets, to use bandpass filters. And so wavelets are a multi-scale sequence of matrices that we're going to multiply our signal by. And they're done by taking a diffusion matrix, which could either be the symmetric diffusion from the talk, or an asymmetric random walk matrix, or actually even some more general family, which we introduced in our paper. And then you raise this to different dyadic powers and you subtract them. So in the spatial domain, rather than just computing purely localized averages, you're looking at averages at different scales, 2 to the j, 2 to the j plus 1, and looking at how does the average behavior differ at different scales of resolution. You can also look at the behavior of these wavelets in the frequency domain. And in a caricatured version of this picture, what you can realize is that the different wavelet scales are supported in different dyadic intervals. And therefore, the wavelets at different scales are going to zoom in on different frequency bands. We also have some theory, which I proved with my co-authors, building off of some previous work by Gamma and Bruna and Ribeiro in the special case where k is equal to t. And you can check that these wavelets are going to be a non-expansive frame if and only if you view the operators on a suitable weighted L2 space. And so given this, you can then construct a graph scattering transform where there's a lot of different variations of the graph scattering transform. I'm going to focus on the one which is most closely related to GCN, where what we do is at each step, you apply many different wavelet filters and then nonlinearities, and wavelet filters, then nonlinearities. And we call this a UP, where P is a path of different scales, J1 through Jm. And then rather than multiplying the previous layer by a matrix A, we compute this UP of the previous layer, and then again multiply by a weighting matrix. And we get what's called scattering channels. And then what Min et al. Do is they introduce a hybrid network that uses both classical GCN channels and also these bandpass scattering channels. And in this way, you are able to compute local averages using the GCN channels, but you're also able to retain high frequency information. And they also provide some theoretical analysis of all of this, where what they do is they look at the GCN channels. And this is both a GCN and scattering applied to the same signal. And if you use the normalized graph Laplacian, then the bottom eigenvector is just a function of the degree. And we can see that in this example, all of the vertices have degree 2, except for these middle 2 who have degree 3. And so when you repeatedly apply GCN, you're effectively projecting onto the bottom eigenvector, where we can see all of the vertices that have degree 2 are basically the same color, which means the signal has the same value, except for these 2 points in the middle, That's because these are like right in the middle of the borderline of the degree 2 guys and the degree 3 guys. And then the degree 3 vertices are their own different color. However, scattering does not oversmooth the signal, and we get different colors at all of the vertices except for the ones corresponding to the intrinsic symmetry of the network. So there's a lot of different variations of the graph scattering transform. The original versions were untrained networks where the feed-forward representation did not have any direct learning in it. This is analogous to the traditional scattering transform, which I'll talk about more on the next slide. The first version was introduced by Zhao and Lerman, which used a different form of wavelets than the ones I introduced a couple of slides ago. Then the wavelets, which I introduced a couple of slides ago, were first used by Gamma et al. In the case where the diffusion matrix was symmetric. And then Gao et al. Applied this to a number of graph classification tasks using asymmetric wavelets. And because because these matrices were asymmetric, they did not carry out the same invariance and stability analysis as was done by Gamma et al. And then what I did, along with the authors from the Gao paper, was we figured out how to generalize the stability analysis to these asymmetric matrices. And the long story short is it's most of the same ideas, but you have to use the fact that these matrices P are not self-adjoint on the normal weighted L2 on the normal L2 space. Instead, you have to find a suitably weighted L2 space and make appropriate adjustments for that, where the weighting corresponds to the degrees of vertices raised to appropriate powers. So these are all like untrained versions of the scattering, which are mostly meant as theoretical models. But there also are fully trained networks, which are very pragmatic from like an actual applying this to real data techniques. There is the hybrid network, which I talked about on the previous slide. There's another variation which incorporates a graph attention mechanism. A third variation which doesn't use dyadic scales, but attempts to learn the scales from data. And then perhaps the most applied version of this is an encoder-decoder network, which uses the scattering for encoder and then uses a fully trained CNN for the decoder. And they use this to generate new molecules hopefully with medical applications. Now, one last slide on scattering before I move to the second half of the talk, which is going to be related to directed graphs. And this is for people who are familiar with the original scattering transform. And to talk about the relationship between graph scattering and graph neural networks is not quite the same as was with the original scattering transform. With the original scattering transform, it was observed, what was observed was that CNNs have the flexibility to learn relatively arbitrary filters, but in practice, the filters learned in the early layers of the networks would resemble wavelets. And so Mallah came up with a wavelet-based model to provide a theoretical analysis of the stability and invariance of these learned CNNs. Now, with graph scattering, we can also use this as a theoretical model for understanding stability and invariance. But there's an additional complication, which is we do not know the approximate class of filters we should be using. With images, we know wavelets are good. With graphs, it's not entirely clear. If we want to promote local smoothness, being similar to your neighbors, these low-pass filters seem to work well. But the argument we're going to make in scattering is that for richer, more sophisticated data sets, that it would work better if you also include bandpass wavelet filters. And so the question here isn't just to understand GNNs. The question is how can we modify the filters used in GNNs to make them more practical for more and more data sets. So that is it for the first half of my talk. In the second half of my talk, I'm going to start focusing on directed graphs. And a directed graph is just like a graph, but every link has a notion of direction. So whereas like an undirected graph might model something like Facebook, where I'm friends with you, that means that you are friends with me. In a directed graph, might model something like Twitter, where you have followers. And for example, I follow Dustin Mixon on Twitter because he has lots of great posts about gerrymandering. However, Dustin is very rude and does not follow me back. So the natural model is a directed graph. Alternatively, there are one-way streets in the world. So directed graphs are a good model for traffic networks. Citations, just because I cite your paper does not mean that you're going to cite mine. Links between websites are not necessarily going to be bidirectional. And there's lots of other phenomenon which are naturally modeled by directed graphs. So if we can extend neural networks to directed graphs, this greatly increases the number of applications for these networks. And unfortunately, the most common approach used by a lot of popular graph neural networks is just to pre-process the data by symmetrizing the adjacency matrix. And while this seems at first glance ridiculous, it actually is reasonable in certain commonly studied situations. For example, if you do GCN on Quora and you're trying to figure out what is the topic of a paper, well, my paper is going to cite data science papers and be cited by data science papers. And so it actually doesn't matter which way the direction is going if you're trying to classify the paper by topic. However, for more general settings, this is not a reasonable method. And what we can show is we're going to apply this to email networks. And we're going to show that email networks where we're going to have emails from a computer science department. And the goal is going to be to classify users based on their role, whether they're a grad student, a staff member, faculty member, etc. And it turns out that people at different roles will have different outgoing email behaviors and ingoing email behaviors. And directional information is going to make a practical difference. Additionally, if you want to do link prediction, even on citation networks such as Quora, what we find is that including directional information does significantly improve performance. And again, this makes intuitive sense because a paper with 1 million references is not necessarily going to get 1 million citations. So given this, our goal is to come up with a flexible machine learning model which can automatically incorporate directional information in a data-driven manner, or in situations like node classification on Quora, automatically choose to ignore directional information if that's the right thing to do. So before I get into the technical details, some further motivation on the data sets we're going to be interested in. We came up with a stochastic block model where we first just developed an undirected graph where everybody was linked to everybody with equal probability, an Erdos-Renyi random graph. And then we assigned directions by dividing the data into 2 clusters. And we came up with the rule that edges will point from cluster 1 to cluster 2 90% of the time and point the other way the other 10%. And so given this, what we can see is that the asymmetric adjacency, the clusters are clearly visible. But if we symmetrize the adjacency matrix, then we completely lose the structure of the graph. We also constructed several more sophisticated versions of similar models, which are usually best represented through metagraphs. So in this graph, there are going to be edges between clusters 2 to clusters 1 and cluster 3. But a majority of the time, edges will flow from cluster 1 to cluster 2, from cluster 2 to cluster 3, although they will sometimes point the wrong direction randomly. And then we also added a small number of noise edges, purely because we were sadistic and wanted to make this make our life as hard as possible, where the noise edges are just completely arbitrary. So that's going to be our main synthetic example. We're also going to apply to a bunch of real-world data sets. And one that I find particularly interesting is the Telegram data set. So for people who are not familiar with Telegram, it is an encrypted messaging service that's traditionally been used by by people in authoritarian regimes to maybe promote democracy around the world. However, in more recent years, it's also been used by right-wing extremists in countries like the West, such as Britain or this. And this data set's actually done by researchers at Oxford, so it's going to focus on the far right in England. And what they did was they looked at the different users on Telegram. And I'm going to assume that most people in the audience are neither freedom fighters in authoritarian regimes or far-right extremists. So the way Telegram works is that there are different types of users. Some are channels, Some are websites. There's also chats, which those are seen in the green dots, but there's not so many of them. And what they did was they looked at the channels, they looked at the websites, and they plotted this, and they observed this core periphery structure where they see there's a few channels at the center of the network, and these will influence most of the websites, which are more in the periphery. And then all the way out in the periphery are a bunch more channels, where right at the center of right-wing extremism in Britain is the Britain First Party. So with that being our motivation, now let's turn to how to define GNNs on directed graphs. So you could attempt to use a spatial approach, and I haven't really talked about spatial convolution, but they are based on using localized neighborhoods. And local neighborhoods are still defined. The set of VJ such that VJ links to VK is still well defined on a directed graph. But the problem with spatial approaches is that this set here is different from the set of VJ such that VK links to VJ. And there's no good reason why you should care more about one or the other. So if you wanted to use a straightforward extension of a spatial network, which is based on computing averages over these localized neighborhoods, you'd have to make a completely arbitrary choice. And so in practice, it usually works better to symmetrize the adjacency matrix. Now with spectral approaches, the key will be to come up with a generalized version of the graph Laplacian. And there's lots of different approaches. We're going to focus on a complex Hermitian matrix known as the Hermitian Laplacian, magnetic Laplacian. So to do this, we first construct a Hermitian adjacency matrix, where what we do is we take AJK and we subtract AKJ, multiply by a parameter Q, and then encode all of this representation to what we call a phase matrix. And then what we do is we symmetrize the adjacency matrix and then multiply by e to the I theta, where this is defined component-wise, both the exponentiation and the multiplication. And so what we do here is we are therefore using polar coordinates to store undirected geometry of a directed network, and the magnitude of the entries in directional information is encoded in this phase matrix. Now there's two special values at Q. If we set Q equal to 0, then theta is equal to 0, e to the I0 is equal to 1, multiplying by 1 doesn't do anything. So this exactly corresponds to treating the graph as undirected. And so we include symmetrization as a special case of our model. On the other hand, if you set Q equal to 0.25 and you do some algebra, you can verify that what we come out is that HQ of JK is going to be negative HQ of KJ if there's a link from J to K, but not a link going back the other direction. And so what this means, therefore, is that a link from me to you is viewed as the exact opposite of a link from you to me. And then other values at Q are maybe somehow in between these two extremes. So given this Hermitian adjacency matrix, we can then construct the magnetic Laplacian. And we use formulas similar to the classical Laplacian, but then multiply by this phase matrix. And we note that both of these matrices are going to be Hermitian positive semi-definite, which strengthens the relationship between this and the traditional Laplacians. And so this structure here is really appealing because we can use polar coordinates to separately capture the directed and undirected geometry. And so to me, it seems actually very elegant to use complex numbers here. The harder question to answer, though, is why this Hermitian matrix and not some other? And we have at least 3 arguments why we think this is a good choice, although the best choice is maybe still an open question. First is this does naturally arise in the physics literature as a model of a charged magnetic particle under flux, which is where the name comes from. So it's not just some contrived thing that was made up by a bunch of math and data science people that was kind of hacked. It's something that exists in nature. And since then, there's been a bunch of research on it by the graph signal processing community. So if we wanted it in future to do theoretical analysis of these networks, we wouldn't be starting completely from scratch. And in particular, it's been shown that different values of Q can highlight different substructures of the graph. And if we're interested in data science applications, this paper here that I'm about to introduce is the first one to use this in a neural net context, but it's been used for lots of other data science applications. We can also do an analysis of its eigenvectors and eigenvalues. On a directed cycle, the eigenvectors are exactly the classical Fourier modes and do not depend on Q, but the eigenvalues do depend on Q. And on a directed star, it's actually the other way around, where the eigenvectors do depend on Q, but the eigenvalues do not. And so what these two extreme examples illustrate is that there's lots of geometric information being encoded both by the eigenvectors and the eigenvalues of this operator. And so given this, we can then define a neural network based on the exact same approach as used in the first half of the talk, where all you do is you take your favorite spectral neural network, you get rid of the regular Laplacian, you plug in the magnetic Laplacian, you make suitable adjustments to deal with the fact that there's complex numbers involved, and then you learn the parameter Q using cross-validation. And given this is a very general formula for extending nearly any spectral network to directed graphs. So I'm going to briefly go some results, but first I'm going to mention a couple of competing methods. Tong et al., what they do is they build 3 different adjacency matrices. One is what they call first order proximity, which is just the symmetrization of the original adjacency matrix. Then they have 2 different second order proximity matrices where they'll say there's going to be a second order link between me and you if we have a common out neighbor. But then they also make another matrix, which is defined the same way, where there's a link between me and you if we have a common incoming neighbor. And given these 3 different adjacency matrices, they then will process 3 different GCN convolutions and use these all mixed together. Other approaches are based on random walks or PageRank, where random walk means you've got a guy here and he can step to any of the neighbors with equal probability. PageRank is similar, but you also randomly teleport to an arbitrary node some fraction of the time. And what Ma did was they used an algebraic relationship between the graph Laplacian random walk matrices and the stationary distribution of a random walk matrices to define a Laplacian on directed graphs. Some limitations of this is that you have to make certain technical assumptions about the graph, and you also have to explicitly compute the stationary distribution, which on an undirected graph is easy because it's a function of the degree of each vertex. But for directed graphs, this is more computationally challenging. And then Tong made a modified version of this talk where they used they replaced the random walk with PageRank, and this does overcome the technical assumptions needed about the graphs, and it does tend to work better. But you still do have to explicitly compute the stationary distribution of the PageRank. So we applied this to a variety of data sets using both spectral methods, spatial networks, other networks applied to directed graphs. And we see that MagNet generally comes in either first or second for all of these real data sets, except for Cora, which Cora, as I mentioned before, is one of these citation networks, which it actually is natural to view as not being really directed. And again, our model does actually select Q equal to 0 there. And so the differences here between MagNet, which is our network, and Shebnet is purely just due to random error in this setting. Telegram is the data set I talked about before. Cornell, Texas, and Wisconsin are email networks where you're trying to classify somebody at one of those universities as either a professor or a grad student. And we can see is that for all of these other data sets, cross-validation chooses Q not equal to 0, and therefore directional information really is important. We also applied this to our synthetic data set with varying degrees of net flow. And again, we see that these are methods which were deliberately designed, these were networks deliberately designed for directional information to be important. So not unsurprisingly, most of the methods which were not designed for directed graphs perform quite poorly. The methods which were designed for directed graphs tend to perform quite well. But MagNet does generally achieve the best performance across the majority of parameter settings. We also looked at a couple of different variations of link prediction. And for link prediction, we looked at two different types of link prediction. One is just, is there going to be some link between a given two vertices? Or direction prediction, where we know there's going to be a link, but we don't know, is it going to point from me to you, or is it going to point from you back to me? And in both variations of these tasks, we again see that our cross-validation procedure is selecting non-valid queues, and directed networks perform better than networks which were not designed to handle directed information. And again, Magnet generally achieves the best performance on most of the data sets. So this is where I'm going to stop. But what I hopefully convinced you of in the first third of my talk is that graphs are a very natural model for tons of different things, and therefore doing data science on graphs is really important. However, most of the common GNNs suffer from two fundamental limitations: the oversmoothing problem and the inability to process directional information. And so I'm suggesting two solutions to these problems. One is that if you incorporate bandpass filters into your network, you can capture more rich variation and high frequency information of signals defined on your graph. And two, you can use a Hermitian matrix and integrate this into whatever your favorite spectral GNN is, and you will instantly get a network which is defined on directed graphs and can properly process directional information. And this is where I am going to stop.
Well, thank you very much. Let's everyone hit that reaction button. And John?